Let's talk about the fundamentals of SN1 and SN2. And I have a unique way of teaching students SN1 and SN2. And what I will say, it involves you taking a bit of a leap of faith. I am going to show you what SN1 and SN2 look like in full detail. What I want you to do is follow along, but also don't put pressure on yourself. Okay, there's a lot going on with these, but I'm going to bring your attention to a few key things as we are going through it. That is what I want you to fixate on. I'm going to show you everything, but there are only a few key details that I'm going to have you fixate on. Okay, and then what we are going to do is we are going to start filling out our SN1 and SN2 comparison chart, which will be a huge asset for you as you continue through this and as you go to the end where you are juggling SN2 with SN1 and E1 and E2. Now, with this here, as a reminder, our general reaction with substitution reactions in general, no matter what, we have a carbon with a leaving group, we have a nucleophile, and what's happening in any substitution reaction is the nucleophile and leaving group are switching places. So without further ado, what I want you to do is take a leap of faith with me, and I will show you the reactions in their fullest extent. Again, don't put pressure on yourself. I'm going to show you the things that matter. Now, take my word for it. This example right here that I'm giving you is a classic example of SN2. You don't need to know why yet. Just take my word for it that this is a classic example of SN2. Here we have a carbon with a leaving group. We have a nucleophile. And the thing that I want you to take away from this classic example and about SN2 is that SN2 happens in one step. It happens in one go. So our nucleophile will come in, boom, and I'm actually going to add in electrons here so that we can keep track of them. And our nucleophile kicks the leaving group out, all in one step. So that's all I want you to care about here. If we are keeping track of the electrons, because that's important when we are starting out, we are breaking this bond. Oxygen's using one of its lone pairs to bond to this carbon, and this bromine is picking up a lone pair. So what we get as a result here, if this reaction goes SN2, is we get this compound with Br minus floating on its own. That's done. That is SN2. We are going to break this down in detail. Now, again, I'm going to show you a classic example of SN1. Take my word for it. This is a classic example of SN1. For the time being, you don't need to know why. Now, the key takeaway that I want you to have about SN1 is SN1 happens in multiple steps. It's a bit more complicated than SN2. So the first step of SN1 is our leaving group leaves. That's it. And when our leaving group leaves, we generate a carbocation. So what we have floating around in solution is we have our leaving group. After it's left, we have our carbocation. If you've gotten to addition reactions before, this carbocation is tertiary. It is not sketchy. You don't have to worry about it rearranging in this case. But don't worry about that right now if you're starting with SN1 and SN2. And so we have this carbocation. And then in a second step, the nucleophile comes in and attacks that carbocation. So we will get something that looks like this compound here if we are keeping track of the electrons. And unfortunately, we are not done. There's still one more step. Things do not like to be charged in this class. So in order to get rid of this charge here, another water molecule will come in and rip this hydrogen off so that it is uncharged. And if you are new to arrow pushing, you may be going like, whoa, 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 where did that extra water molecule come from? Here's the rule. If you ever see water in a reaction, you can assume it is in excess. It is the universal solvent. There's always a lot of it. So what we get as a result here is this compound. And now, again, for the time being, don't get too wrapped up into this, okay? The big takeaways that I want you to have is SN2 is one step, SN1 is multiple steps. And here's the other thing that I want you to take away. At the end of the day, these two reactions have the same net result. Here's what I mean by that. We started out with a bromine on a carbon chain, and we replaced it with an OH. We started with a bromine on a carbon chain, and we replaced it with an OH. So in these two examples, SN1 and SN2 have the same net result. But what I want you to notice is outside of that same net result, they go about getting that result completely differently. SN2 is efficient, you get that net result quickly. SN1 is not as efficient, you get that net result a little more slowly. So that's what I want you to take away for the time being. The key to being able to understand what is going on with SN1 and SN2 relies on something that you haven't seen for a while. You haven't seen it since Gen Chem. So I need to remind you about something. The key to understanding this is putting it in terms of the rate law of the reaction. And I know me bringing that up right now may get you a little anxious because it's been a long time since Gen Chem and rate laws are not fun. It's not extreme knowledge, it's just very pointed knowledge that we need here. So just as a reminder, the equation for the rate law of any reaction is K times the concentration of the reactants to their power. Now, the rate law is governed by what we call the rate determining step. So what we care about is the rate determining step. And what I want to remind you about is that the slow step of a reaction is the rate determining step. Okay? So the key to understanding this is being able to see the rate law for each reaction. So let's figure out the rate law for both of these and show you how knowing the rate law helps you understand what's going on. So with SN2, we have good news. There is only one step for SN2. So by default, this must be the rate determining step. It's the only step. So this is the slow step. So to determine the rate law, we need to include the reactants that are involved in the rate determining step. The way that you can tell that a reactant is involved in the rate determining step is if it participates in the arrow pushing for that step. So let me ask you here, does our nucleophile participate in the arrow pushing for the rate determining step in SN2? And the answer is yes. So it must be included in the rate law. Let me ask you the same question about the leaving group. Does our leaving group participate in the arrow pushing for the rate determining step of SN2? The answer is yes as well. So if we are determining the rate law for SN2, the rate law is going to include both the carbon with the leaving group and the nucleophile because both participate in the rate determining step. Now, let's ask the same set of questions about SN1. So here, what I'm going to let you know is the first step where you generate the carbocation is the rate determining step for SN1. So generating carbocations is difficult. This is our slow step. So let's ask the same set of questions here. Does our carbon with our leaving group participate in the rate determining step of SN1? Well, it's involved in the arrow pushing, so the answer to that is yes. So it's included in the rate law. So let's include it in the rate law there. Notice, let's ask the last question. Does our nucleophile participate in the rate determining step of SN1? Well, it's not involved in the arrow pushing in that first step. So it doesn't participate in the rate determining step, and therefore our nucleophile is not included in the rate law. Our nucleophile doesn't come in till the second step. So let's put everything together now. Let me ask you a question. How many molecules are present or participate in the rate determining step of SN2? What you will notice is that there are 2 molecules that participate in the rate determining step for SN2. That's why it's called SN2. How many molecules participate in the rate determining step for SN1? Only 1 molecule participates in the rate determining step for SN1. That is why it's called SN1. No professor spends any time explaining that to you guys. So that is really important info to have, because a lot of times students will say, well, why is SN2 one step and SN1 is multiple steps? It's because the 1 and the 2 are referring to the rate law. And what I will tell you is understanding the rate law for these processes is the key to everything. So in our comparison chart here at the very top, we are going to put the rate law for both of these processes. So again, the rate law for SN2 contains both the carbon with the leaving group and the nucleophile. The rate law for SN1 only includes the carbon with the leaving group. So what we're going to do is we're going to start adding layers to this now and start relating everything back to our rate law. That is the most important thing. Let's relate everything back to our rate law. So first things first, one thing that you can keep track of that you've already seen, one major difference is SN2 happens in one step and SN1 happens in multiple steps. And another difference that is important, that is subtle, is SN2 has no carbocation, whereas SN1 has a carbocation. Add something here just in case your class is in a different order and you've seen carbocations before. Since SN1 has a carbocation, rearrangement is possible. But if you haven't talked about carbocation rearrangement yet, don't worry. We will get to that in a later video. Now, I'm going to ask you a series of questions. I want you to think about this in terms of our rate laws here. Okay? So I'm going to ask a very, very important question, and it doesn't matter if you know what I mean by it. So let's ask it. Which one of these reactions requires that you have a strong nucleophile? I want you to think about that for a second. Which reaction requires a strong nucleophile? You don't need to know what a strong nucleophile is. We will talk about that in the next video. But hopefully what you see is the nucleophile is involved in the rate determining step of SN2, so it matters greatly. The nucleophile does not participate in the rate determining step of SN1, so the nucleophile does not matter for the speed of the reaction for SN1. So by that token, SN2 requires that you have a strong nucleophile, and SN1 is totally cool if you have a weak nucleophile. Because the nucleophile doesn't participate in the rate determining step, You could have the strongest nucleophile in the world, and it wouldn't matter. Next up, I want to ask you, which reaction requires that you have a good leaving group? You don't need to know what a good leaving group is, but think about this for a second, based on those rate laws. And what I want you to see is that both reactions involve the leaving group in the rate determining step. So there's one key similarity between SN1 and SN2. And I'm going to put this in big letters. Both need a good leaving group because the leaving group is involved in the rate determining step. Perfect. We are going to talk about one more detail, and then we're going to fill out the rest of the comparison chart in the videos to follow. So for both of these reactions, before we head into the next set of videos, I want to leave you with a key phrase for each reaction. So the key phrase that I want you to remember for SN2 is that since it happens in one step, your nucleophile needs space to kick out the leaving group. So since this happens in one step, our nucleophile needs a lot of space to come in and kick out this leaving group. We want this leaving group to be as unhindered as possible. So with this, we like uncrowded leaving groups. So primary leaving groups are better than secondary leaving groups, which are a little bit more crowded, which are better than tertiary leaving groups, which at the end of the day are way too crowded to do an SN2 reaction. So just to show you a little bit of that right now, of how to figure out primary, secondary, or tertiary, in this example here, you look at the carbon with the leaving group and how many carbons are directly attached to this carbon with the leaving group. Well, directly attached to it is only one carbon. So the example I gave you is ideal. This is a primary leaving group. Okay? The key phrase that I want you to remember for SN1 is this. The whole name of the game for SN1 is we want to generate a stable carbocation. So we see the opposite trend of the leaving group. And I'm going to put here, this is in terms of the carbon with the leaving group. This is in terms of the carbon with the leaving group. We see the opposite trend of leaving group types with SN1. So ideally with SN1, we want a tertiary leaving group, which would make a tertiary carbocation, which is more stable. Then we would want a secondary leaving group, and then very last, a primary leaving group. And so primary leaving groups generate primary carbocations, which is not good. So primary leaving groups would generate something too unstable to do an SN1 reaction. So as we wrap this video up, here's what I want you to see. Everything hinges upon knowing your rate law, because the rate law explains what's going on in these steps here and the trends that we see with these reactions. And two, what I want you to see as well is if you have a primary leaving group, you're pretty much guaranteed to go SN2. If you have a tertiary leaving group, you are pretty much guaranteed to go SN1. But they overlap at secondary leaving groups. And you best believe that your professor is going to hammer home that gray area of, well, if you have a secondary leaving group, which reaction happens? That's what we're going to figure out in the next videos. We're going to start identifying what a leaving group is, what they look like, what a nucleophile is, what a strong nucleophile is, what a weak nucleophile is, and then we're going to fill in the rest of the chart. So thanks for taking that leap of faith with this. We have this comparison chart started. In the next video, we are going to do the 4 baby steps of SN1 and SN2. We are going to look at them in isolation, fill out the rest of this chart, and then after that, we are going to put it all together. And if you follow the process, it's going to work like magic. By the end of this video section, you will be very good with SN1 and SN2. So let's get the ball rolling. Let's look at those 4 baby steps. I'll see you in the next video.